everybody. Thank you all for coming. Today we're very honoured to host a special seminar on Friday to Professor James Dyke. James Dyke's an academic writer and author, associate professor in Earth System Science, and assistant director of the Global Systems Institute at the University of Exeter. We've also got here that he's a fellow of the Royal Society of Arts, fellow of the European Geosciences Union, and serves on the editorial board of the Journal of Earth Science System Dynamics. And he's going to be talking to us today about the parable of Daisyworld to the fairy tales geoengineering. Thank you, James.
Thank you. Morning. Thanks for coming. Quite surprised there are so many people on it. Hey! I was going to say, you look like this is Friday, 10 o'clock in the morning. That's the energy we need. I have not had enough coffee yet, but we'll have a coffee afterwards. How's that? I can lure you with caffeine. Who's heard of Daisyworld?
Yeah.
Yeah. Who's got firm opinions about Daisyworld or the Gaia hypothesis or Gaia theory? Any biologists? Any evolutionary biologists? Okay, we're relatively safe. Who's heard of geoengineering? Yeah. Well, if you haven't, you soon will do. I mean, that's part of my argument. So Daisyworld was initially proposed as a parable, as a thought experiment, as a kind of way to try and think quantitatively about something called Gaia. But I'm really here to basically blow some more shade on geoengineering because I seem to be doing quite a bit of this at the time. Now, a very influential report was published in 2009 by the Royal Society, and I read it at the time. But it's only been very recently that I realised the direct link with Daisyworld. And this is what I was talking to you about yesterday, because this is an image from the front cover. So this is the publication I'm talking about, Geoengineering the Climate, Science, Governance and Uncertainty. So the 2009 lead author was John Shepherd. I think he was at the University of Southampton at that time. An esteemed authorship list. And that's the front cover. And at the time I thought, that's a nice picture, you know. But it even says on the immediate page afterwards, this cover image, so this is just a quote, this cover image comes from the Daisyworld model developed by Jim Lovelock and Professor Andrew Watson. Andy has just retired from Exeter, which shows you just how long ago they were proposing the original Daisyworld model. Anyway, and it illustrates the tight coupling between climate and biosphere through the connection between surface reflectivity and temperature. And this is what I'm going to explain later when I talk about Daisyworld. This is the principle on which geoengineering by reflection of solar radiation is based. And probably the reflection of solar radiation is the way in which we are going to deploy geoengineering, in my opinion, right? If anybody wants my opinion, I'm going to give it to you. And I think that's what is going to happen. It's not absolutely guaranteed, but it's probably going to happen. And Daisyworld has been instrumental in drawing attention to the tight link between the Earth's surface, climate, and presence of living organisms. That's the parable. But really, I think we might be making or learning the wrong lessons by applying Daisyworld to an issue such as solar radiation management. Okay, so the talk is going to proceed by answering three questions. Three questions. Anyone? Right. Okay, look, never mind. Most of my cultural references are about 30 years out of date now. Anyway, what is Gaia? What is Daisyworld? And what is overshoot? Because overshoot is where we get into the arguments for geoengineering. Okay, so what is Gaia? Let's just remind ourselves. Jim Lovelock, back when he was this handsome young fellow, if you don't know much about Jim Lovelock, he was a remarkable figure, certainly quite controversial at times. Big proponent of nuclear energy. He used to like to scandalise green or progressive politicians by promoting nuclear fusion and fission, rather, as a viable form of energy. This is back when he was a postdoc at the Jet Propulsion Laboratory. He was hired by NASA to think about how would you design an experiment to detect life on Mars, because that's where they were thinking of going next, right? And Jim's argument back at the time was you don't need to spend billions of dollars to put a rover or a robot on Mars to determine whether or not it's got life or not. All you need to do is look at the Martian atmosphere. And if the Martian atmosphere is the kind of atmosphere that you would predict just from the pure geology and where the planet is in relation to the sun, then you can be pretty sure that there is no widespread biosphere, because biospheres unavoidably alter their atmospheres. They produce atmospheres which have, let's say, high entropy, or they're far from equilibrium. And so really you just need a spectroscope and you just need to look at the atmosphere. And he wrote that up back in 68, I think. A physical basis for life detection experiments, and this is pretty much what we still do in the context of much of our astrobiology aspirations. We're already imaging planets around other stars. We're already beginning to infer what the composition of the atmosphere is, and therefore to what extent is disequilibrium some kind of potential function of a chemical process that we would describe as life. Anyway, the recognition of life is that necessarily perturbs the environment. It produces these kind of high entropic states. Okay, let's consider the Earth, right? And the Earth is important and interesting. As far as we know, the Earth is the only planet in the known universe that does have life. Certainly the most complex system in the known universe. And in many respects, the Earth has been kind of lucky, right? We kind of lucked out in the cosmic roulette, and there's anthropic selection principles that we can evoke to sort of begin to explain that. But certainly when it comes to Mars, that's too far away, it's too cold. Or when it comes to Venus, it's maybe a bit too near to the sun, it's got runaway greenhouse gas. So there's this kind of notion of the Goldilocks zone. And again, this is a kind of a well-established principle in astrobiology. If you want to look through, if you want to try and detect habitable planets, then there's a habitable zone, which is essentially a function of the luminosity of the star and how far away you have to be before it's too hot or too cold. Okay, certainly Earth was lucky to be in the habitable zone. But if you go back far enough in time, so here we are today, and you go back about 4.6 billion years ago, which is the origins of the Earth and the other rocky terrestrial worlds in the solar system, you will find that the temperature on the surface of the Earth was within the range that we consider compatible with life, but also was Mars, right? So there's pretty abundant evidence there were oceans of liquid water on Mars. There's always been tantalizing clues there could be some kind of microbial life on Mars. There are certain abiogenesis arguments or theories which life actually emerged on Mars and was transferred to Earth through asteroid collisions, and so we are essentially Martians, right? But what happened is that whilst Earth remained within the habitable zone, Mars deviated. It's too small to hold on to its atmosphere. It got very cold. It lost all its water, evaporated off into space. It got very, very cold. Venus went the other way, of course. It did dip into the habitable zone nearly, but then this is the runaway greenhouse gas. When people talk about runaway greenhouse gas warming on Earth, then climate scientists and astrophysicists are very exercised, because no, that's not what we mean. This is a runaway greenhouse gas atmosphere. This is an atmosphere on the surface of that planet. The temperatures and pressures are sufficient to melt lead. So hopefully that's not going to happen on Earth anytime soon. In about 1 billion years, when the sun becomes much larger, then yes. Okay. So life unavoidably affects the environment, but could life, through its affecting the environment, also be regulating it in some way, such that it's not just luck that maintained Earth's habitable trajectory, right? And this is the origins of the original Gaia hypothesis. So here's Jim, a little bit older, and here's a very young Lynn Margulis, who at the time was a postdoc, an early career scientist who was becoming increasingly known for her quite forthright views on biological evolution. She championed the idea of endosymbiosis, which is now largely established, of how we manage to evolve complex things such as eukaryotes. She had a marvelous and very interesting career, but I don't have much time to talk about her, but we need to recognize her involvement in the Gaia hypothesis. And basically he said, look, Earth just hasn't been lucky. Maybe in some respects, the coupling between life and the planet produces some kind of thermostatic function, not like thermostat, right? But you know, there is the fact that the Earth has remained within the habitable zone isn't just chance. There's a mechanism which involves life itself. Okay, so when you talk to evolutionary biologists about this, it goes down like a bucket of sick, because they fucking hate it, right? Because biological homeostasis, for example, in your bodies, you're sweating, you're cooling, you're dilating all these capillaries, these really highly refined kind of adaptive responses. How do you create such things? How do these things exist in the universe? It's through Darwinian mechanisms, or then neo-Darwinism, the modern synthesis of evolution. That's how you create complex systems that can, for example, perform homeostasis. Well, there hasn't been some kind of mother Gaia like pumping out all these little baby kid planets, and there's been some kind of selection. So what it means is that a relatively narrow interpretation of Darwinian mechanisms can't explain how a complex planetary scale homeostatic entity could come into being, right? So this largely, I would think, explains why there was so much persistent vociferous pushback against the original formulation of the Gaia hypothesis. I think it's also the case that in his communication, in his work, Jim actively tried to antagonize people and upset, particularly evolutionary biologists. But I would argue we've come a long way. So some of the work that I've been involved in, certainly the work that Tim Lenton, who's also Exeter, has been involved in since the 1990s, which, well, how could a mechanism like that emerge on a planet in the absence of Darwinian selection? And it's kind of like a kind of stochastic selector type system. You've got an endless cycling of evolutionary innovation, which unavoidably affects its environment. If it destabilizes it, such as a great oxidation event, maybe a few billion years ago, which produces a mass extinction event, it drives the system outside of the bounds of habitability, and then basically you've got this massive reset. And you keep on doing that until you fall into a stable attractor where you have some kind of persistence. And what I'm going to talk today is about where this kind of persistence might emerge from in a very crude or simple interpretation, which is, what is Daisyworld? Because that was the original motivation, right? How could this work at all, right? 1982, back when Andy Watson was doing his PhD with Jim Lovelock, and they wrote this paper, Biological Homeostasis of the Global Environment, the Parallel of Daisyworld. I first read this paper here at Sussex. Oh my God, like 20 something years ago when I did the Masters in Evolutionary Adaptive Systems, which was led by Inman Harvey. And Inman used to run a class, I can't remember the name of the class, right? And basically he would give a lecture. Was it?
Yeah.
Hello.
Hello.
Oh, I didn't reckon that.
Yeah.
You don't look a day over. Yeah. Although doesn't parenthood affect?
Yeah.
Yeah.
That had a big effect.
Yeah. It weathers. In a good way.
Yeah, absolutely.
Yeah. Right. Anyway. Right. Okay. So it's the A-Life module then. And every seminar, he would pick on one or two people. You'd have to read the paper, you'd have to present the paper. And he gave the Daisyworld Gaia lecture. And when he was giving it, I thought, this is complete bollocks. This is just nonsense. This can't possibly work. And then for the seminar, he didn't get us to read this one. It was one, the Saunders paper, the rain control one. Basically, they published it in 82 and then...
That was his paper, right?
No,
No,
it wasn't Inman's. It was Peter Saunders. A number of Peter, I think about 10 years later, he basically did the analytical solution, right? Because they numerically integrated this thing and he solved it. And as I was reading this thing, I became radicalized. I thought, my God, there's something in this actually. This is really interesting. And so I ended up pivoting to do quite a bit of that, and that's how I got to, the first postdoc was basically astrobiology. Because I got very interested in planetary evolutionary dynamics. Anyway, since 82, people were writing a lot about these Daisyworld models. You could get Daisyworlds that were doing all sorts of different types of dynamics. And back in 2006, a bunch of us, including Tim, Hal, he is now at Exeter as well. Graham's in Edinburgh. Andrew Wood is in York. We said, look, we're going to draw a line under all this. We're going to say, look, everyone's been fiddling around with Daisyworld models. This is the definitive take on Daisyworld model, and we're not doing more. And then, of course, we continue to publish lots more papers about Daisyworld. But if you do want a snapshot, this is a pretty useful one, I would argue. So what is Daisyworld? Okay, this is how I would describe it. Imagine an Earth-sized planet orbiting the same distance, like 1 astronomical unit away from a sun-like star, and it's grey. And on this planet, you've got very simple life forms. I never asked Jim why he called them daisies. I can't remember. And I actually asked Andy Watson this, and he said he's got no idea either. But, maybe it was the 70s, right? So they're daisies. They're kind of light-coloured life plants and dark-coloured plants. And you seed the planet, right? So you've got tiny little seeds on the surface of this planet. the temperature of the planet is some kind of environmental variable. We call it just TP, right? That is a simple function of basically insolation, the amount of energy received on the surface of the planet, which is a function of its brightness or its albedo. And you make the initial assumption that the environment has some sort of effect on life, right? So the very crude kind of lock and key. Life is adapted to its environment. The environment shapes life, so it kind of fits this idea of a kind of ecological niche. And they did that by assuming that, just like all types of life, life can only inhabit a particular range of environmental variables. So if you've got temperature, when you look at plants on Earth, usually they don't really grow much below 5 degrees Celsius. Above 40 degrees Celsius, it's a bit too hot. But somewhere in the middle, you've got an optimum growth rate, right? So you've got this kind of peaked, or Inman used to like to call them hat functions, if you remember that. He was obsessed with hat functions. And that's, so your growth rate is some kind of function of temperature. But this is where it gets exciting. So this is more kind of JMS, John Maynard Smith. I went past JMS building earlier. So I was here when he was here. Wonderful guy, if you remember him. Incredibly foul-mouthed. Do you remember he would give lectures and swear all the time? He was quite... Anyway, the idea of fitness being a function of frequency, right? You know, frequency-dependent selection. It's the fitness of something isn't just entirely driven by the environment, it's also driven by the frequency of those animals in the population. But there's also another important observation in which life necessarily affects its environment. So this was Jim's original kind of postulation. That's how we conduct astrobiology. Nowadays, we talk about this in context, let's say, niche construction, you know, classic ones being, you know, beavers and dams, you know, or when it comes to planetary scale niche construction, the technosphere that humans have built over the last few thousand years or so. So that's a coupled co-evolving system. In Daisyworld, that was captured by the life having an effect on temperature. So as the proportional coverage of black daisies increases over time, then because the planet is getting darker, it's absorbing more energy, temperature's going to go up. And the inverse for white daisies, because they have a higher albedo than the grey planet, if you increase the coverage of the white daisies, then the temperature is going to go down, right? So this is where it gets exciting. Because imagine now that it orbits a star like the sun, which increases in brightness over 4 billion years, right? So the sun's about 25% brighter than it was when the Earth was formed, 4.6 billion years ago, but temperatures have remained within that habitable zone. And as the sun gets brighter, do you see that? Let's see that again. As the sun gets brighter, yeah? So yeah, don't worry. Make sure you got the glasses on for this next slide. It's a humdinger. As the sun gets brighter, you would imagine here, the temperature on the planet basically goes up. Of course, these are non-linear, you know, but you can kind of linearize everything. It doesn't really change anything. But the principle is more energy from the sun, more insulation, more heating, planet temperature goes up. Right? However, everything changes when you put those little black and white daisy seeds on, right? Can you imagine what's going to happen? Okay, well, it looks like this. The star's going to get brighter, the temperature's going up, but then suddenly the planet goes darker, then it gets lighter and lighter and lighter and lighter, and then it reverts back to the grey state. Yeah. The dashed line is the abiotic or dead planet. With the presence of black and white daisies, there's sudden temperature increase. Then temperature is maintained, or in this linear example, it's regulated exactly. And then it ends a period of habitability and snaps back to that abiotic state. Let's just see that again, right? So sudden increase in temperature and darkness, it's becoming lighter and lighter and lighter, and then we snap back. How does that work? Well, what's happening is that it's the differential coverage of the black daisies which have a warming effect and the white daisies have a cooling effect. So the original kind of plots looked a bit like this. You've got luminosity increasing on both of these horizontal axes. Planet temperature here, no daisy state, sudden increase. Temperature actually slightly decreases because of things that aren't really all that interesting, and then snaps back to the abiotic state here. And that's because initially, as soon as the black daisies can grow, as soon as it begins, the temperature ends up in that habitable zone of about 5 degrees Celsius, the black daisies begin to expand. As they expand, they expand over a much faster timescale of which change of the sun. You can imagine essentially that over Bartic timescales, the sun is essentially fixed at a particular luminosity, which means that the coverage increases, which means it absorbs more energy, which means the temperature goes up, which means the data coverage increases. It's a reinforcing feedback loop, which ends up with maximum daisy coverage of the black daisies. But as you increase temperatures further, you're driving the temperature of the daisies beyond their optimum, so they start to decrease. But now the white daisy coverage increases, and the balance of those two systems mean that you're actually pushing planetary temperature in an opposing direction towards what happens to be the optimum for the daisies. And that is the Peter Saunders paper of 1994. There you go. Right. Yes.
Sorry.
I will allow questions at this time.
Right, you might be about to mention this, but if I remember correctly, what's important here is not that the black and white daisies have specially tuned parameters for their homeostatic zones, but that their local effects on the temperature are what make them. You might be about to say,
I'll allow it. Yes, I was going to say that, but
Okay.
as in all things, Simon, you say it much better than I do.
I don't think it is.
Right. So the point being, so Peter basically solved it, but he also argued that really this is an example of rain control, and that the direction that these life forms are having on their local environments is the same they're having on the global environment, and they're opposing it in such a way that you kind of regulate it in a quite tight. You call it integral rain control. So when I was doing my DPhil here in, I was very interested to understand that as a simple control system. And so you've got insulation, you've got some kind of, if you've got a system imagining like this, then the kind of the elements are some kind of system which is driving the insulation or the energy that's interacting through albedo, which is some kind of function of the life forms that affects temperature of the planet, which affects the temperature of the daisies. Or more simply, you've got some kind of exogenous driver that's having some impact on an environmental variable which affects life, which necessarily affects it again, right? But there's always, look, these are models. You know, you give me a model, I can get it to do anything. You know, enough terms. I can give you elephants. I can give you dancing elephants. I give you elephants dancing with daisies. So a lot of my interest was, how can we really understand what are the core elements of? So what can you take away from this original Daisyworld model to try to understand? And there's been lots, I'm not going to talk about it at all because I realise I've spent far too much time on this bit. But much of the work I did later was to try to understand how could you get rain control emerging in a system which you don't prescribe. Because if you make the white daisies have a cooling effect and you make the black daisies have a warming effect. What if you have the white daisies have a warming effect or the black daisies have a cooling effect or something else? You just randomly have effects, and you can do that, right? So this is work I did with Ian Weaver when he was in Southampton. So he was my PhD student in Southampton, and basically it's very robust finding. If you have a sufficient population of the space, these are kind of just like random Gaussians, and they can either increase an environmental variable or decrease an environmental variable. The population effects, when you've got these kind of zero crossings here, these are your stable attractors, right? And so the assumptions you need is that life affects environment, life is affected by environment, and there is a sufficient amount of, let's say, biological diversity, and that it's inevitable that you have these kind of attractors. Now, where it gets interesting on planetary scale homeostasis, it's all about time scales of operation, right? But let's just side skirt those quite important caveats. What I thought was interesting though is when you've got, let's imagine you've got a daisy world with 4 daisies rather than just 2, it starts to do things like this, right? It starts to do things that look actually a little bit like Ashby's homeostat. And I called it a daisy stat, which at the time I was quite proud about because it was a concatenation of Daisyworld and Ashby's homeostat. That's my idea of fun, right? But in non-trivial mathematical terms, it's not equivalent. But if you know anything about Ashby's homeostat, it's got these 4 elements, and you drive outside of its range, and it undertakes this kind of uniselector Well, that's what happens in a 4-element Daisyworld. This is basically the activation of the uniselector. It's thrashing through new states to basically fall into and find another stable state. And it will do that until it does. And then you can maybe scale up to think about how planetary scale homeostasis might work. Now, I'm not arguing that is the end of the matter, right? But I would say that we can begin to think a little bit more precisely about the kind of mechanisms that might be operating at a planetary scale. It's a bit of a tough ask given the timescale, but maybe even certainly ecosystem level scale, right? But this is the interesting question. What is overshoot? Who's heard of overshoot? Climate overshoot? Who's heard of net zero? Right, you should all put your hands up. This is being recorded. My argument is you're going to hear an awful lot more about climate overshoot because that's where we're going. How much longer have I got? What, 20 minutes? Maybe 15? Yeah? Okay.
20.
Okay, so this is what we're meant to be doing. So this is the UNFCCC, the United Framework Convention on Climate Change, 1992. To combat the dangerous human interference with the climate system. It was already apparent in the 1980s, 1970s that the planet's getting warmer, CO2 emissions are going up, CO2 concentrations going up because of the burning of fossil fuels. If we were to continue to do that, that's probably a really bad idea. So let's stop the dangerous interference. It's only been relatively recently, like the early 2000s, late 1990s, that we can quite definitively look at the relationship between, this is cumulative CO2 emissions. So this is the total amount of CO2 we put into the Earth's atmosphere since, well, pretty much the Industrial Revolution, the first and second Industrial Revolutions in the United Kingdom. And because CO2 stays in the atmosphere for so long, hundreds, if not thousands of years, it has a kind of radiative forcing effect. What matters is not so much when we put it in, but just the total. So you can imagine you've got a bucket of water and you just keep putting in more water and the water level is going up. And therefore, if the cumulative emissions are going up, the concentrations in the atmosphere, your partial pressure of CO2 is being pumped up and up and up and up. So when you plot cumulative CO2 emissions with warming, so maybe the temperature anomaly or how much warmer it is since pre-industrial periods when concentrations are 270 something ppm, you can kind of, over a sufficiently long time scale, it looks kind of like a straight line, right? I mean, it's quite, it's pretty robust, such that we can be quite confident that if we want to limit warming to a certain amount, then there's a certain amount of CO2 you can put into the atmosphere, which is where we get our carbon budgets from, right? So if you want to limit to warming to well below 2 degrees Celsius or 1.5, then you've got, well, no carbon budget left, basically, maybe about 2 years worth or something. But if you want to limit to maybe 2 or 3, and these are the SSPs, the shared socio-economic pathways, which are one way of trying to think about the different types of scenarios which would produce the change of cumulative emissions that will result in a particular kind of warming, right? I would summarize that as fuck around and find out, right? If you want to fuck around with the climate, right, then you're going to find out that the consequences through increased forcing and the bad things that a more energetic climate system is likely to do, like blow over houses and, sea level rise and stuff like that. It was in 2015, which would be 16 years ago now, that the international community agreed that dangerous, the find out bit that we don't want to find out, is well below 2 degrees Celsius, which since then we now understand is like 1.5. And that means there's an available carbon budget. If we had started mitigation in 2000, for a 66% chance of staying below or even at 1.5, then we would have decarbonised at 4% or something. Pretty ambitious, but doable. And of course, the longer you leave it, the smaller the carbon budget becomes, therefore the more rapid the rate of mitigation. Robbie described it as in 2019 you do monumental, and then 9 years basically the budget's gone, right? I just want to point out that the Paris approach in net zero never actually argued for the immediate phase out of fossil fuels. It was an amazing international treaty, and it provided numerous on-ramps to countries like the United States, because the United States would never sign up to any kind of treaty that opposed the rapid phase out of fossil fuels. And one way they, I suppose, tried to soften the blow somewhat is that, of course, by the middle of the century, we're still going to have aviation with kerosene burning, and we're still going to have cement and steel producing CO2, but we'll just offset those things, right? So you've got no rapid phase, the rapid fossil fuel phase out. Yes, we will give you net zero promises, but somehow we will fathom out how to take that carbon dioxide out of the air, which is where we get net zero. So net zero just isn't kind of offsetting, but using science-based targets which come from the very notion of carbon budgets themselves. So the science of net zero is absolutely robust, right? And that's how we get carbon budgets. Where I've been a little bit critical is how that has been interpreted by policymakers, because if you provide policymakers with a way of removing carbon or promising to remove carbon at some point in the future, then why would they actually implement very hard political decarbonisation now, right? So it's perhaps no surprise that when you look at net zero promises by 2030, it's actually lots of carbon offsetting. And I'll be honest, my own university has a very ambitious net zero target by 2030, right? And I was part of a working group for the university that actually said, this relies on carbon offsets and you shouldn't be offsetting your emissions because we have no confidence those emissions are actually having any material impact on the climate. What are you going to do about it? So is the university going to do something quite radical and see how it's going to meet its 2030 target, or might that 2030 target evolve in some way? I'll let you think about that. Just to point out that if you have any climate skeptic friends, you know, those uncles you have to endure, retired engineers for me, I find, who tell you that it's all a hoax, there's nothing to worry about. Get them to pay attention to what's going on in the insurance industry, because there are places which are becoming uninsurable, and there are some insurance companies that are becoming increasingly worried about solvency, given the increasing costs of extreme climate weather. Okay, and yes, it also produces an awful lot of suffering. Anyway, why do people continue to say that 1.5 is still alive? Have you heard that? 1.5 is still alive, right? Because the argument is that we can recover back to 1.5 by the end of the century. So this is where geoengineering is going to come in, right? So we're going to overshoot 1.5. We're going to continue to burn fossil fuels, but this bit here, we're going to increase carbon removal, carbon dioxide removal through a portfolio of approaches. Have you seen the recent preprint about BECCS? It's scandalizing some people. All right, maybe in the discussion we'll talk about that. So now we're in overshoot. So temperature is going to exceed 1.5 or any amount, really. But the deployment of CDR is going to drag temperatures back down. I describe this as the wacky races, because if you've got an idea on removing carbon dioxide removal, you can probably find some philanthropic organization that's going to throw some money at you. And I say that with all the bitterness and envy that because I mean, look, some of this research is really interesting and good, and some of that actually happens at Exeter, and I do think it's actually pretty cool. The alkalinity stuff they're doing, you know, the ocean acidification, where if you try and combat that, you can also sequester more CO2 in the oceans. Biochar, that improves the quality of soil, but also pyrolysis can hold up carbon for longer. Habitat restoration, so restoring the forest we've destroyed by allowing ecosystems to recover, that seems to be a really good idea. Unfortunately, most of carbon removal, or CDR, is afforestation, which is kind of the industrial scale planting of alien monocultures, which can often be catastrophic for biodiversity, also water security and food security. Enhanced rock weathering. Do you remember your carbon silicate cycle from geography? You know, the long-term geological control, the weathering of mountains, which get it to hurry up a bit, right? By basically blowing up entire mountains and then crushing the rocks and putting on farmland. Algal blooms, every now and again somebody does that. They throw 500,000 tons of iron filings in the sea, and, you know, because it's meant to promote algae. Or this one, this is where most of the money's happening at the moment. That's direct air capture. The like air conditioning units, strip out CO2 from the air, compress the gas, put it down, probably in disused oil and gas fields, right? Of course, the problem with all these things, especially that one, is one of entropy. I would describe these require phenomenal amounts of energy, because you're taking concentrated carbon dioxide and you're releasing it, which we measure it in parts per million, and then you've got to put an awful lot of energy to literally compress that back and You know, I think Gibbs had something to say about it, but you know, it's getting a lot of money, right? And it's got to work, right? This has got to work. The argument is we don't know how to do it, but we have to do it. Why do we have to? We have to because we can't do it. We're in an awful lot of trouble. Therefore, it will have to work. Well, what if it doesn't, right? So this is overshoot plus. We're going to exceed, we're going to do CDR, but then we're going to do geoengineering to shave. So temperature shaving, peak shaving is how it's often described, at least in public. So this is your carbon dioxide removal. This is your peak shaving, and this is solar radiation management. So remember Daisyworld. Daisyworld temperature on the planet is a simple function of albedo and insolation. As the sun increases in brightness, what happens on Daisyworld is the temperature is regulated because the planet becomes lighter and lighter and lighter as a result of the interaction between the black and white daisies. Well, what if we could do that? So hence why Daisyworld was on the front cover of that 2009 paper. Most of it is about making the planet lighter. There are also proposals for increasing the long wave radiation to get out more, increasing the optical window through deleting clouds. I like to call it deleting clouds, like go around kind of with an eraser or something to let more energy out. But most of it, it's about making the planet's surface whiter, genetically modified crops that are much brighter, mirrors or painting buildings white, putting something in the wake of ships to make very reflective, long-lasting bubbles, pumping up water to increase the nucleation of clouds over the sea, disco balls in space, large sunshades at the Lagrange point between the Earth and the Sun, data centers in space. You've been reading about data center space?
That's about to say.
Two birds with one stone. You can do all your ridiculously expensive compute, and because you need these solar panels and radiators to dissipate the heat, that's where you get your sunshades from as well, right? And I joked about that. And then the following week, there was this, could this be a solar radiation management technique? So again, missed the funding window. But most interest, certainly most of the work in a climate context, when we're doing like GCMs, climate modeling, is in this one. This is sulfate aerosol injection. We know this works because every now and again a large volcanic eruption puts a few million tons of sulfurous compounds and other dust and crap right into the higher portions of the atmosphere. It stays for a few years, eventually rains out, basically kind of falls out. But these sulfurous compounds, they form very highly reflective little kind of bubbles, particles, and that can reflect quite a lot of the incident radiation from the sun. Pinatubo from 92, was 92? No, 91. 91. The eruption in Pinatubo, half a degree Celsius, right, for a couple of years. So basically, they looked at that and went, we'll have some of that, right? So how would we? Obviously, it's not some kind of Bond villain. They're not trying to actually detonate volcanoes. What they would do is they would, well, they would be proposed to shoot large cannons with sulfurous compounds in the atmosphere, but probably it'd be something like a converted fleet of wide-bodied commercial aircraft. They'd be converted into tankers, and they would kind of spray kind of sulfuric acid or something into the higher kind of troposphere, right? As high as you can, what's it, 40, 50,000 feet or something. Probably in the higher latitudes because it is more effective in the higher latitudes. But for reasons I'll maybe talk about later, that's not entirely sure. Now, of course, if that's all we did and we didn't do anything to combat emissions, which are at all-time highs, then it makes as much sense putting air conditioning on when you're in a fire, right? So obviously, nobody proposes we do, you know, CDR and SRM and continue to have ever increasing greenhouse gas emissions. Actually, some people do, but they won't say that in public. So what this means then, the UFCCC, if it was finally to embrace geoengineering, is we're going to combat the dangerous human interference with the climate system by interfering with the climate system. So we kind of accidentally interfered in the wrong way, but now we are going to intentionally interfere in the right way. And we're going to do that in a very clear kind of control systems approach. We're going to try and put our hand on that planetary thermostat and direct it in such ways that we want to keep it not within the habitable zone, which is quite broad, but we're probably talking within a couple a couple of degrees Celsius, right? The level of the fidelity of control that we are hopeful we're able to affect on the climate system is really quite narrow. Now, often it's proposed as some kind of emergency measure, right? So I do want to talk about, I'll talk maybe later about how tipping point narratives are being used to promote geoengineering research. That's something we're becoming very interested in. But it looks a bit like this. You know, you've got business as usual. Obviously, we can't do that. So we'll do some mitigation, right? But mitigation alone is still by the end of this century, and certainly by the end of the 23rd century, where we're well above 4 degrees Celsius. I mean, it's like game over, in my opinion. If you've got 4 degrees Celsius warm by the end of the century, I mean, we're literally cooked. But what's interesting in many of the discussions I have, the rate of mitigation is somehow fit. There's a speed limit. There are structural limitations for how that first, second, or nth derivative that can only bend so much, right? So finance, I was talking to David about a meeting out with some finance people, World Bank kind of central bank people. And for them, this is thermodynamics, right? There are iron laws of finance. Right? If you want to finance a transition, you want to do decarbonisation, it just won't go any faster, right? Okay, so then what do? Well, we do CDR. Okay, well, we don't know how to do that. Yeah, but we'll figure that one out. So when we talk about, well, what about thermodynamics? Yeah, but this is finance, right? Scientists figure out the thermodynamics, right? Leave the grown-ups with their finance. Anyway, let's say we can do some CDR, but that's still not enough, right? So the idea is it's going to take some time for CDR to be deployed. So the SRM, this is what's going to shave off the stuff above 2 degrees Celsius, or maybe even beyond, where things get really quite gnarly. And then with some adaptation as well, right? Because adaptation is a function of exposure and the vulnerability to that hazard. Then you can actually get above this thing, which is the impacts of suffering. So climate policy has always been mitigation. It's always been adaptation. This gets the majority of the coverage, but adaptation was always important, given there are vast differences in vulnerabilities, right? But now what we're going in overshoot plus, climate policy is a function of mitigation, adaptation, CDR, and increasingly, I argue, it's going to be SRM. Right? Because obviously we can't do that any faster. Right? What's this got to do with Daisyworld? Well, I mean, I kind of telegraphed the bad pun and the punchline, I think. Fossil fuel use is increasing temperature. And of course, the thing you want to do if you want to maintain temperature is you need to rapidly phase that out, right? But there's a speed limit in which you can do that. And we don't want to do it too fast, but fortunately, there's something else. Oh, if only we could do something else. What could that be? Well, it could be ways to change the albedo. It could be, well, let's do solar radiation management. And I would argue this is exactly what we are doing. Unabated fossil fuel use, if we just continue this, then basically you've kind of got this, this line here. But what we can do is essentially temperature shaving, right? So in I think in a real literal sense, I think Daisyworld does make sense. Temperature shaving is the technology, the deployment, the planetary scale albedo modification, which allows you to extend the habitable zone. So the interesting thing about Daisyworld was that daisies can only really live within this kind of bound here, right? In this kind of temperature range here. And if you map that temperature range to luminosity or brightness of the sun, it's actually quite narrow, right? It's only like about there. But when you've got the daisies, especially when you've got the white daisies, you can just drag that on, like for maybe, 1 billion years or so. Of course, the problem, one of the issues that we got with geoengineering is what we call termination shock. What happens if we stop, right? What happens if we were to continue to emit carbon dioxide and we'll do temperature shaving for 10, 20, 30, 40 years, but then for some reason we would stop doing that? And people say, well, of course we wouldn't stop that. Why would we stop that? I don't know. Maybe there'd be like a global energy crisis because of a war in the Middle East or something. Or maybe there could be like a global pandemic, which means that we're not able to continually put planes into the atmosphere. One of the supposed benefits of sulfate aerosol injection is if you stop doing it, its effects end quite quickly within a couple of years. Probably most of those effects within the first 6 to 12 months or something, the way it just rains out. What this means, you end up having a very large increase in temperature, and all you biologists and ecologists know that it's not just the magnitude of kind of change, it's the rate of change. And so if you have a very sudden increase in global planetary temperature, that could be potentially catastrophic. But I would argue what we're doing in a geoengineering context is that geoengineering is extending the habitability of fossil fuels. That's what it's for, right? We need to be clear about that motivation. It is there to ensure that we do not have to undertake a rapid mitigation, right? And there could be very valid reasons for why that is, you know, structural, financial, political, but let's call it what it is. I'm not going to linger too much about this because I think we're getting into the discussion. So I've been interested in the kind of academic practice around geoengineering, but also more kind of think tank and policy wise. I mean, look, it might not work, right? It might not do anything, right? So we think it's going to have a cooling effect, but it doesn't. And if it's had a mitigation deterrent effect, if it's lured us into the sense that it's actually going to be a positive for the climate, then obviously that's not great. One of the greatest concerns in the science climate community is it's going to do bad things. If you put it in the northern hemisphere, then it might start to do something to the Southeast Asian monsoon. It might start to move Sahel climates. It might start to, through the process of teleconnections, produce all sorts of things that causes harm to certain people in certain places, right? And perhaps most importantly, in my opinion, it's geopolitically, it becomes very, very gnarly, right? We can't even agree to allocate a relatively easy to understand carbon budget thing when we're arguing over who gets which sides of the slide. When you have a situation in which nations begin to unilaterally, and whenever people seem to wargame this, that's what happens. Nation states just decide to pull the trigger on this. When you do that in a climate which is already being degraded in terms of international cooperation because of increasing resource conflicts and forced displacement migration, you're just throwing potentially even more gasoline onto the fire. Okay, I'll skip that bit. And the last bit, it is also obviously somewhat hubristic to think that we can undertake certain measures just to shave off, right? So this is just a little plot from the work that I did with Ian 13 years ago, right now. And this shows that when you've got, Daisyworld was always like one environmental variable, temperature. Well, this is two environmental variables. So this could be, I don't know, like temperature and salinity in the sea, or temperature and the concentrations of a gas or something. There are some, you know, life is now a function of two environmental variables. And then you can plot these very simple spaces. And when you have those random populations, which can increase or decrease or increase, you know, you end up with these little attractors all over the place. And we used to love noodling around with this stuff because these very simple dynamical systems do things really quite counterintuitive. For example, if you want to kind of think, well, I want to get to this kind of state, right? So let's increase, and I'm over here, or I'm over here, and I want to kind of increase the environmental variable there. You can find you'll end up being entrained in completely different directions. Or the system looks as if it's going somewhere, but the timescales are such that it had sufficient time to evolve or be going somewhere else. Your immediate interventions, your crude application of some kind of lever, means that the system is going to behave in ways which are continually surprising. This is obvious, right? But none of this has ever been discussed in the context of geoengineering. It's very much a kind of progressive, linear, shave off here, very kind of emergency measure in order to alleviate some of the worst case scenarios, which increasingly involve things like tipping points, right? And that's it. Off you go then. I finished. Thank you. Monty Python and the Holy Grail, for anyone who's not like 50. Do we have time for questions?
Yeah.
I think we do have time for that. Yeah, about 5 minutes, 10 minutes.
So it seems the danger with the basis for traction in the end is either, so you're not in a one dimension, you're not in two dimensions, you're in n dimension space. And the idea of, as you say, being heuristic enough to think you understand that system, and can either you shave stuff off and you stay in the same basin of attraction, or you move out that basin of attraction and you have no idea where you're going to end up.
Okay, so there's this. So Dave and I were talking yesterday about the idea of to what extent the planet, the Earth's climate system has very clearly defined attractors, right? And I think that's a very interesting question. What's perhaps more important are not planetary scale attractors, but also subplanetary, regional scale dynamics, because that's where people live. That's where nation states are. That's the most important teleconnection with regards to the governance, you know. So Simon was talking about, what if we do this over here? Was it Azerbaijan or something? And then some other country, whatever it was, you know. So what if the United States deploys and then there's some kind of extreme weather event in China, right? And we know there are teleconnections across the climate system. Okay, that's one. Yeah. But there's also teleconnections that link the climate system to the biosphere, right? And some of those biosphere systems are important because they sequester carbon, but also they're important because they are part of food systems, you know. Those kind of dynamics, you have to, so when we're doing these kind of experiments, we inject here and see what happens. The way in which they're evaluating the consequence of those are obviously very, very simple because the interactions are incredibly crude, right? And when, I don't know when either you talk to people about this, but the impression that I get is obviously it's with a heavy heart. Obviously we don't want to do this, but the consequences of us not doing it are just unimaginably bad. And we'll just have to see how it goes. Right? You know, kind of suck it and see. And with enough monitoring and stuff. But then, I mean, I guess we've just got to hope you haven't inadvertently entrained certain elements of the system into a state which, for those people in those regions and those places, those nations, could be quite significantly worse than global environmental change in the variable of, you know, average temperature or something. Those kind of discussions are not non-existent, but very poorly articulated and sometimes done, in my opinion, in incredibly bad faith. Right. Yes, please.
Oh, sorry. Yeah. So when you showed the original graph, you showed this quite linear relationship between the amount of CO2 and the temperature, right?
Oh, yeah.
And so, you know, I guess, you know, people worry about these feedbacks like the permafrost and so on. But is that reflected in that linear thing, or is it we're just not in a regime where those kind of feedbacks are enough to change that linear trend thing? Also, you know, the kind of emission of carbon is not being uniform across the globe, right? The West kind of industrialized first.
Mm-hmm.
So has that had any kind of local, these kind of local effects rather than global effects first? Or is
Oh, right,
it not
okay.
strong enough in forcing to do it?
Well, it gets globally well mixed. There's that nice video, right? It shows, I mean, they've got a simulation all the way down
Mix
to
really
like
quick, right?
smoke stacks, and you can see them. And then you've got these longer, you've got this diurnal kind of things that the forests are absorbing, but it's a really well globally mixed gas, right? And so that's also one of the things that concerns in the context of adaptation and also geoengineering. If you're only if we're all collectively trying to avoid dangerous climate change, and there's very few places on Earth that would actually think that climate change is a benefit. I mean, there's an argument that maybe Russia is going to benefit from because you're going to have increased productivity of farmland and stuff or something. But almost every country has agreed we don't want to do that, right? So it doesn't matter where the carbon comes from, you know, Boston or Baltimore or, you know, Bangkok, right? Geoengineering is quite different because nation states would do it probably not just to try to reduce the global average temperature, but to reduce maybe some particular extreme weather event that's happening. So it's kind of related to sort of weather modification. And of course, adaptation is place-based as well. And so there's always a lot of concern around mitigation deterrence through adaptation. If you tell policymakers in the UK, you know, sea level rise 2 meters, but, you know, we'll just need a bigger Thames barrier, then they'll probably, you know, because they'll look at, you know, emission reduction rates and the drag on economic growth, and they'll make that kind of calculation. When it comes to this, well, I mean, look, one of the things, as your man here is going to tell you at length, is that lots of the tipping points they're worried about, the time scales of those are, you know, not years, but decades, centuries, even millennia, right? So, you know, when the ice sheets go, and in my opinion, they probably are on the way out, right? But we're talking thousands of years. There's some tipping elements that could actually even have a global cooling effect, like shut down an ocean currents. But the regional consequences, certainly for the UK and Europe, are, you know, potentially catastrophic. There was, yes, please.
Yeah,